Calorimetry is an experimental technique that involves the measurement of heat changes associated with physical or chemical processes. In laboratory, such changes are measured in a calorimeter. These measurements are generally carried out under two conditions: at constant volume, QV, and at constant pressure, QP. The experimental technique of calorimetry actually involves two steps. First step is the determination of heat capacity of a calorimeter. The second step involves the determination of the change in temperature during the completion of the reaction, assuming that it is an insulated system and no heat is exchanged with the surroundings. Let us first discuss the measurement of heat change at constant volume, or the internal energy change, delta U. The reactions that can be most easily studied under constant volume conditions are the combustion reactions, and the apparatus used for this purpose is called the bomb calorimeter. It consists of a sealed constant volume steel container known as the bomb, in which the reaction takes place. The bomb can withstand high pressures. A known mass W grams of a combustible substance is placed in the bomb, and oxygen under high pressure is introduced into the bomb. The sealed bomb is then immersed in a known amount of water contained in an insulated container. As the container is insulated, there is no heat exchange with the surroundings, and the reaction process is adiabatic. This whole setup is called the bomb calorimeter. The sample is ignited electrically, and the heat produced by the combustion reaction is absorbed by the water surrounding the bomb. The increase in temperature of water, delta T, is noted, and the heat produced is calculated using the equation QV is equal to CV multiplied by delta T, where CV is the heat capacity of the calorimeter. The measure of a bomb calorimeter's heat absorbing property is called its heat capacity. Each bomb calorimeter differs from all others in its ability to absorb or release heat. The heat capacity of each bomb calorimeter is determined experimentally. Heat capacity of the calorimeter is determined separately by igniting a known amount of a substance, whose heat of combustion is already known, in the same calorimeter. And CV is equal to C multiplied by M, where C is the specific heat of water and is equal to 4.184 joules per Kelvin per gram, and M is the mass of water. Actually, heat capacity of the calorimeter or the system is the sum of heat capacity of the bath, that is, water, and the heat capacity of the bomb, that is, the metal. Water has high value of heat capacity as compared to the metal of the bomb. Thus, heat capacity of the metal is neglected, and the heat capacity of the calorimeter is taken as the heat capacity of only the bath. This QV expressed above is the heat evolved when combustion of W grams of the substance takes place. Since heat of combustion is defined as the combustion of 1 mole of a substance, therefore, the expression for molar heat of combustion becomes molar heat of combustion is equal to CV multiplied by delta T multiplied by M by W, where W is the mass of the substance taken and M is the molecular weight of that substance. As the above reaction is carried out in a closed vessel, therefore, heat evolved is the heat of combustion at constant volume and is a measure of internal energy change delta U. Let us now measure the heat changes at constant pressure. To measure the heat changes at constant pressure, a device known as a coffee cup calorimeter is used. These calorimeters are open to the atmosphere. So, these measure heat changes at constant pressure. This calorimeter is a formed polystyrene cup partially filled with a known volume of water and fitted with a stirrer and a thermometer inserted through the lid of the cup. When a reaction occurs in the coffee cup calorimeter, the heat change is measured in terms of the change in the temperature of the system. Heat flow in the system is calculated by using the relation Qp is equal to specific heat multiplied by m multiplied by delta T, where Qp is the heat flow in the system, m is the mass of water in the coffee cup in grams, and delta T is the change in temperature. Specific heat of water is taken as 4.184 joules per Kelvin per gram. Therefore, the formula for calculating molar enthalpy delta H substance is delta H is equal to m multiplied by specific heat of water multiplied by delta T divided by N, where N is the number of moles of the reacting substance in the system. It is important to note that when heat is absorbed or evolved by the system at constant pressure, we are actually measuring changes in the enthalpy. Therefore, delta H is equal to Qp. In an exothermic reaction, heat is evolved and the system loses heat to the surroundings. Therefore, Qp as well as enthalpy change delta H is negative. Similarly, for an endothermic reaction, heat is absorbed by the system from the surroundings and therefore Qp as well as the enthalpy change delta H will be positive.